All right, OCLSC, who wants to go under the hood? So we have, thanks, that's a great response. We have a trio of FileMaker staff presenting here today, starting with two FileMaker server engineers who were critical key architects of the features that we're going to be talking about today. Starting with Murali, who's a 9-year FileMaker vet. We have Ming Chen here to my right, who's in his 2nd year of FileMaker. And my name is Ryan Manook. I'm a solutions consultant at FileMaker, and I'm in my 11th year working at FileMaker. All right, so we're going to start our journey today by exploring the database engine, and we're going to see how we implemented changes to improve scalability. We'll then follow that up with a look into startup restoration, which it's a powerful feature on its own merit, but it was especially important as a reliable support for this new scalable design. And then from there, we're going to take what we learned, and we're going to chat about different scenarios and use cases to help you best determine how to use FileMaker 18's performance. Now, while we're diving through the database engine, I just want to keep in the back of our mind today's visionary keynote. So we definitely planted our flag as a future-forward thinking company. And for us to realize that success, it was imperative for us to make changes to FileMaker's underlying database engine. So in FileMaker 18, you're seeing some of the first server-related steps to support this vision. And we're introducing a new architecture called page-level locking. Now, previously, there was a multi-threaded element, but it was only available across multiple files. Page-level locking brings multi-threaded processing within each file. So to help demonstrate the power of this multi-threaded processing, Ming Chen and Murali are going to join me, and we're going to each deliver our separate pieces of the content simultaneously. So we'll get you out of here in 15 minutes, and you'll have 45 minutes of your DEF CON back. Does that sound good? OK, all right. You don't want to be here with us? OK. All right. Without further ado, allow me to introduce Murali.
Thank you. So I'm going to talk about the FileMaker database engine. Basically, if you look at the database engine, there are two logical components. The first one is the key value store. Basically, the whole data in the FileMaker is organized as a key value store. So how do you basically control access to the key value store from multiple sessions? And at this lower level, we have what's called a B plus tree. That is how we actually physically organize the data in the database. So if you look at the two components, there are two different mechanisms to control access to the database. For the logical key value map, we use logical locks to control access. And for the physical B plus tree, we use physical latches, also known as the page level locking. So I'm going to describe in more detail in the next few slides. So just a brief introduction, what is this FileMaker database engine? It's a typical relational database storage engine. And it, like other storage engines, it supports multiple concurrent user sessions. What type of data we store in the FileMaker database? Mainly, there are two categories of data. One is actually the user data, like, for example, all the tables and rows, columns, and what's the data in that. But more importantly, there is also the metadata, which the database engine has to maintain. This includes information like what are the table names, what are the column names, and what are the types of the columns, and what kind of relations we have between the tables. So all that kind of information. This is what we commonly call the catalog information. And also, particular to FileMaker, we have other pieces of data like all the user scripts and layout information, all those things. So these are the two types of information that we store in the database. So I just want to give a very broad overview of what are the different layers in the FileMaker database engine. There are basically like 4 layers on top of the actual physical database. At the top layer, we have the database engine, which is the interface to the rest of the FileMaker components like FileMaker Pro or all those things. Below the database engine, we have what's known as a key value store. So pretty much every piece of information in the database is eventually stored as a key value pair in the database. And the key value pair is also basically it's a logical abstraction. It's like a hash table in C++, that kind of thing. So it has to be actually mapped, implemented by a real data structure. And in FileMaker, we use one of the most popular key value stores, which is B plus tree. So basically, the key value store is actually organized as a B plus tree underneath. And below the B plus tree, we have what is known as a page cache. The main idea is that a typical B plus tree index in a database can have millions of pages of data. And of course, we cannot accommodate all those pages in the main memory. So we basically stage the relevant pages of the data in the page cache. So basically, the page cache data structure helps the B plus tree to basically load and unload the pages from the disk into main memory. So from the database engine, we move one level down to the key value store. So very brief introduction. So what is the key value store? Basically, it's like a very simplistic interface. Both keys and values are byte strings. It's very simple. But unlike other key value stores, in FileMaker, the keys are not flat keys. They're basically what we call hierarchical keys. So each key has a kind of a very simple structure. So each key can be broken down into multiple subkeys. So for example, I just showed a typical key. It has like 6 subkeys. And so starting from the left to right, we can organize like the subkey number 1, 2, like that. So the reason why is why we are actually using subkeys is that so any key value store, any ordered key value store, it has to implement basically an ordering function, because between every pair of keys, they should be like we should be able to tell which key comes before the second key. So in the case of FileMaker database engine, we don't compare the whole keys. We compare one subkey at a time, starting from the left. So for example, if you say take that key example key, right? So we first compare the first subkey FF00, and if let's say if the keys match, then we move down one level and then compare the next subkey like that. So that's how we basically implement the comparison between keys. So you might be wondering, like how do you reconcile between a relational table and a key value store? So I'll just give a very simple example. So it kind of motivates like how we are mapping between the relational world to the key value world. So I just give a very simple hypothetical table with two columns. It has 4 rows. Of course, the first, the column is the internal column. It's not actually defined by the user. But it has like a column called name and another field called city. It has 4 rows. So now I'm going to show how this information can actually be translated into a key value store. So if you look at it, so I'm showing a very simple encoding scheme. So let's say that we encode the database like with value 01. And let's say in the database file, there is table number 2 called 02. And then, so for example, if you look at the very first key in the key value store, it has like, if you look at it, there are like 5 subkeys. So the first leftmost subkey tells it's like database 1. And then the next subkey tells it's like table number 2. And then there is a special meta key saying that, OK, I'm going to now give all the rows of that particular table. And then the next subkey says that it's 01, which actually means it's like row number 1. And then the last subkey tells it's column number 1. So what is the value for that particular key is the value John, right? So like that. So, but what is more interesting is that this is all very common. But if you look at the last entry in the key value store, we see that basically we are implementing, OK, let me go back to the previous table. In this table, we are also having an index on the secondary index on the field called city. So now we want to maintain the index for the field city. So if you look at this key value store, in the last row, we have like 01.02.indexes. So what it means is that in database 1, table number 2, for the indexes, the field number 2 with a value of San Jose has a set called 2, 4. What does this mean is basically if you look at here, for the field value of San Jose, there are 2 rows which satisfy that property, 2 and 4. So that's why we are actually storing a set called 2, 4. Of course, internally we represent that set as a bitmap. It's very efficient. So we can even store like millions of rows. It's very compact and very simple. So this is how we are not only we are able to store primary indexes, but we can also store secondary indexes. So basically, it's very simple. We are taking a very complicated concept like a relational table, and we are mapping that into a very simple interface called a key value store. It's not only it's very simple, but it's also very powerful. Pretty much every information in the relational world can be mapped to the key value store. So now we move one level down. So we're going to now explain a little bit about what is the API for the key value store. So it's a very simple API. So it has like the most common operation is get the value of a key. So you execute the get method and it look up the key value store and it will tell you the value of that key. And the second most common operation is put a key value store in the key value database. And the third one is like you want to delete a particular key. But what is more interesting is there is something called seek and scan, because as I mentioned before, this key value store it's ordered key value store. So not only can you do like point lookups, like look up a particular key, you can also execute range queries. That means you can say that get me all the keys in the range between start key and end key. So that also we can execute very efficiently. So for that, what you do is you do a seek to the first leftmost key that you're in your range. And then after that, you do a scan, like you execute a next operation until you reach the end of the range. So this is a very simple API for the key value store. Of course, this whole key value store is just a logical abstraction, but it has to be implemented by some real data structure. So we use one of the most popular on-disk key value stores, what is known as B+tree. So B+tree, it's a very brief introduction. All the data is organized as nodes or pages, what we call pages. And there are basically 2 types of pages in the B+tree. One type is known as the index page, and the second one is a data page. So basically the purpose of index pages is to provide very quick access to the actual key that you're looking for. And the data page actually contains the real actual key value data. So, I mean, for example, if you need a database, only in the data pages all your data is stored. The key value, the index pages are only used to speed up access to the key value pairs. So one brief detail here is that internally, for us, everything is a key value pair, but the payload differs from index pages to the data pages. So in index page, the payload for a key is actually the child page number. So, and then in a data page, it's actually the user data. Just very brief idea behind how in a B+tree you actually search for a particular key. So in the index page, basically you have, as I told before, you have again a range of key value pairs in an order. So if you want to look up for a particular key in the B+tree, if you look at 2 adjacent entries in the index page, it will tell you which page number to look for the particular key. So for example, if you have 2 adjacent pairs called key K1 and page number P1, and key K2 and page number P2, and let's say if you are looking for a key between in the range between K1 but less than K2, then you look up in child page number P1. So that's how you keep traversing from the root page until you go through all the, descend through all the index pages, and then finally you reach the data page where you actually look up the value of the particular key. And also internally, basically, we have two more operations in the B+tree. The first one is what is known as page splitting. So basically, what happens is when you try to insert a particular new key value pair in a database in a data page, Let's say if the page is already full and the particular page cannot accommodate that new key value pair, so then what we need to do is we have to actually split the data page into two pages. So we try to split approximately in the middle of the thing so that half the key value pairs will go to the left one and the remaining go to the right one. But since we are creating a new page, we should actually add an index to the new page in the parent index page. So that is what is known as splitting the data page. Similarly, the converse, like if let's say if you're trying to delete a key value pair, and then let's say after you delete it, the page becomes kind of like too small in the sense that more than half the page is free, and we don't want to actually fragment the B plus tree because it will be a waste of space. So what we try to do is we try to see if we can merge this page with one of the adjacent data pages. And if it is possible, we actually merge two pages into one single page and then remove the index entry in the parent index page. So they're kind of nicely, they complement each other. So this basically shows a typical B plus tree. So it has like 3 levels. At the top level, you have the root page. And then there is the intermediate level of index pages. And finally, at the lowest level 0, we have all the data pages. So if you look at it, like for example, in the index pages, the key value pairs are the keys, the starting keys, and the child page number. Whereas in the data pages, we have the key and the value of the key. So that's how. And then another thing which you can notice here is that there are 2 types of links here. One is like the solid links are the actual links between at each level. For example, if you look at the data page between page number 4 and page number 5, you see 2 links, right? So page number 4, the next page is page number 5. And for page number 5, the previous page is page number 4. So for example, if you're doing a range query, you can start at page number 4. Then you don't just have to traverse the next links to get all the subsequent keys. So the dotted links only show the parent-child kind of relationship. So that's why there are 2 different types of links here. So now, a very brief introduction to what is a page cache. As I was telling before, a B plus tree is a disk-based data structure. So what that is, all the pages of the B plus tree cannot be accommodated in the main memory. So when the B plus tree data structure needs to access some of the data pages, it has to actually call the page cache to request the page cache to actually load the page from the disk into the main memory. So there are 2 operations. One is like pin a particular page. So you say if you execute the method pin a particular page number of a file, the cache manager will look into the file and load the particular page into the main memory. So once you pin the page, it is guaranteed to be in the main memory until you are done with that page. Either you are looking up some key value pair or actually modifying it. And once you're done with the page, you can actually unpin it so that if needed, for example, if the memory cache is full, that particular page can be evicted out of the memory and some other page can be loaded. So now, I briefly explained how we are actually physically, first we are organizing your data as a logical key value store, and then we are mapping it to a physical data structure called B plus tree. Now, I'm going to explain how now when concurrent users are actually trying to either read or modify this logical key value store, how we are going to control access to the database. So there are 2 different mechanisms. For the logical key value store, we use a mechanism called logical locks, which I'm going to explain. And for the physical B plus tree, we are going to use the actual page level locks. So why do we need these locks? So there are 2 different concepts here. For the logical key value store, we need to maintain the consistency of the logical key value store. So one simple example is, let's say, if you want to add a new row to the table, and let's say one of the fields is also indexed in that table. So both these operations should be atomic. That means that when you add a new row, so you also need to add the index for that row into this thing. So either you add both or you should not add. So that is what is called logical consistency. So that can be actually achieved by using logical locks. And then the physical integrity of the B plus tree should be protected because we have to maintain, we have to basically make sure that the B plus tree is really well formed. That means that all the pages are properly linked and every data page is at the same level depth from the root page and all those things. So for the logical thing, for the logical consistency, we use logical locks. For the physical integrity, we use page level locks. So that briefly like summarizes what are the two different types of concurrency control mechanisms. So logical locks. The logical lock, each lock is actually associated with a particular key. So one minor detail here is that since our keys are not flat keys, they are actually hierarchical keys, we use what is known as intent lock, but that I won't go into the detail for that. But pretty much the idea is that the last subkey of the logical key, it has to be locked in one of three modes. So what are the three different types of locks here? So one is basically a read lock, or also known as a shared lock. And the second one is update lock. And the third one is exclusive lock. Intuitively, the idea is that multiple concurrent sessions can acquire a read or shared lock on the same key at the same time, no problem. Because multiple people can be reading the same key, they won't block each other. But then, like, let's say if one session actually wants to update the value of a key, so it is not done in one step. Like, you don't directly get an exclusive lock. It's actually a two-step process. So first, we actually get an update lock on the key. And then once you're ready to modify and commit the value of the key, you change that to exclusive lock. So to summarize, read locks are used if a session is using only a read-only query, it will only get read locks on all the keys that it is going to look up. And if a session actually wants to modify the value of a key, you start with an update lock on that particular key. And then once you modify the key and you're ready to actually change the value, you upgrade that to an exclusive lock and you change the value. So that's how we control access to the logical key value store. So just to give a broad picture here, I'm showing what is known as a compatibility matrix. So this actually tells you like when it is possible to get what kind of lock. So on the vertical column here, we have what is known as the granted thing. So let's say a session already is granted one particular type of lock, and then another session makes a request, then we are telling whether that request can be granted immediately or not. So for example, let's say one session has the read lock on a particular key. And if another session actually makes another read request on the same key, yes, it can be granted. But let's say if the session is holding a read lock on a key, but another session makes an exclusive lock request, it cannot be granted because you have to wait until the read lock is done. But if you see, for example, if you see one session is already having an update lock on a particular key, and the request comes from a read lock or update lock, they can be granted. I mean, if a request comes from a read lock, it can be granted, but another update request cannot be granted. So that's how we're actually protecting that. Only one session at a time can update the value of a particular key. But of course, one session already got an exclusive lock on a particular key. Nobody else can do anything on that particular key until this key is done. So that's how we actually control access to the key value store. So now we move down to from the logical level to the physical B plus tree level. Just like we protected the logical key value space, we also have to protect the B tree with page level locks. But here the locking is much simpler in the sense that there are only two types of locks, only read or shared lock and exclusive lock. And the granularity here is locking one page at a time. So multiple sessions can actually lock the same page with a read lock. That's fine. But only one session at a time can actually lock a page in the exclusive mode at a time. So now we actually come to the actual page level locking protocol. So how do we actually execute 3 different types of queries? The most simple one is a find request, also known as a point lookup. So all you want to do is you want to look up the value of a particular key. So how do you do it? So you start with the root page of the B plus tree. You log the root page with a read lock. So like multiple sessions can do the same thing. Now, once you log the root page with a read lock, you look up what is the next level index page you need to access from the root page. And then also, we look up that page. Once you look up the index page, you have to read log that page. You're still holding the lock on the root page. So once you log the index page, you can release the lock on the previous root page. So that is how it basically proceeds in a lockstep fashion. You're not holding the locks. As soon as you log the next level index page or data page, you can release the lock on the previous level. So like that, you keep going down the tree until you reach the data page, and then you look up the value of the thing. So it's very simple. But what is more interesting is it's not a point lookup, but you want to look up a range of keys. So let's say you say that I want to look up all the keys in the range of key K1 to K2. So here, basically, you do the same protocol as before. You first look up the left subkey K1 until you reach the data page, same protocol. But now, instead of moving from top to bottom, you move from left to right. So let's say there are 2 scenarios here. Basically, if the second end key is also in the same data page, you're lucky. You're already done. No more thing to be done. But let's say if the key K2 is not in the same page, then you have to actually move horizontally from left to right in the data pages. So for that, you actually log the next level data page and then release the lock on the previous data page. So now we are moving from left to right. So you keep repeating until you reach the end key in the range. So now, a little bit more complicated case. You're not actually reading, but you actually want to modify the value of a key value pair. So here, now, instead of locking the page in the shared mode, you do exclusive lock on the root page. And then you look up the next level index page, child number for that. Then also, now he actually lock the next level index page also in the exclusive mode. So, but now, unlike before, you cannot release the lock on the current index page. What is the reason for that? The reason is that potentially when you reach a data page and if you try to add a key value pair, the page might be full and you might actually need to split the page. So in that case, you actually have to add an index in the parent index page. That's why we cannot release the locks as before. So you have to keep holding all the locks until you reach the data page. But there is an exception here. If, let's say, at a particular level, like, for example, the second level from bottom, if we know that the particular index page has enough space to actually hold a new index page entry, then you don't need to hold locks above that level. So that way, we're trying to make it a little bit more scalable in the sense that we're not holding the whole B tree locked. We're only holding locks only up to the level that we need. So once after you insert the data in the actual data page, you can release all the remaining locks. So the complementary case is it is similar. It is basically you want to delete a key value pair. So it's very similar. You start locking the root page in the exclusive mode. Again, keep traversing all the index pages down the tree, not releasing the locks until you reach the data page. And then once you find the key value pair in the data page, you can delete that thing. Just like the insert case, here also, if you know that at a particular level, you're not going to propagate the merge of 2 pages above that level, you can release all the locks above that level. But once you are done with the delete operation, you can release all the remaining locks. So this is how basically it's a very broad overview of how the page level protocol works. So basically, what is the idea behind this page level locking? This is like a first step towards actually providing full ACID transactional capabilities. So, and Ming-Chen is actually going to talk about startup restoration, which is also another step. He's actually implemented what is known as redo logging. And eventually, you want to implement full redo, undo logging, and make the FileMaker database engine very robust, very efficient, and scalable database engine. So that is the future roadmap for the database engine.
Hello, hello. Thanks, Morali. You guys wanted to underhood, so we took you to Tree City. All right. So obviously, multi-threading, it opens up new doors for performance. But at the same time, it's essentially opening up more and more request sessions. And when you're in an environment where there's potentially all these requests writing to the disk, you want to be in the most reliable environment as possible. So that brings us to startup restoration. And honestly, I mean, the idea of restoring a database from an unexpected shutdown or failure, that's just really common in database deployment. So we'll show you how it works in FileMaker. So here's a really quick 1-minute high-level introduction to startup restoration for those of you unfamiliar with this feature. So startup restoration, it's a reliability feature that you can enable or disable through the admin API. And by default, out of the box, it is enabled. So what happens, all changes that you make to your hosted custom apps, they're also going to be written to a startup restoration log. Then, in the event of an unexpected shutdown, what's going to happen is that when FileMaker server starts up again, it's going to look to that startup restoration log, and it's going to attempt to bring your hosted custom apps back to their last consistent state. Pretty straightforward, right? So, as we mentioned, we have Ming Chen with us here today. He was one of the key architects in the design and implementation of this feature. And he's really excited to be here with us today just to give you a really, really quick demonstration of how startup restoration might look in your deployment. So Ming Chen.
Okay, I want to use login to admin console. Okay. So to check the database status, okay. So right now, okay, so this database will be used in this demo. Okay, so they all looks in good state. Okay, so now we are all set. Okay, to start the test, first I'm going to launch my FileMaker Pro and open my test database. Okay, so this is a FileMaker app that we use for testing PLL actually. Okay, so it supports multiple users. Okay, so for this demo, I'm going to set it to 5 users. Okay, so what it does is going to make 5 user connections to the database server, and it's going to do all kinds of write, as this is here, to the database. Okay, the purpose is to keep FileMaker server busy, and while we try to crash it. Okay, so I'm going to run it. Okay, you can see in the activity monitor, the process is busy writing to the database. Okay, so now I'm going to try to crash it. Okay, ready to go. So here I use Q-9, okay? So this will kill the database server immediately without any exit handling. So this is more like a server crash condition, okay? So now it's killed. So next, I'm going to restart FileMaker server. Okay, started. So let's log into admin console again and check the database status. Okay, here, okay, you notice there are 3 databases are in gray state. So that means they didn't get open. Okay, so there's something wrong. So let's go check the event log for error messages. Okay, so we do see some error message here. So there are 3 databases, okay, could not be opened, okay, and they may be damaged, okay. So without startup restoration, what we can do now is we can use FileMaker Pro to recover the files manually, or we can copy from the backup, okay. So now I'm not going to try to recover it, okay. So we're just going to move on to the case with startup restoration, okay. So now I'm going to enable startup restoration. I'm going to use my admin API tool. Okay, so this is the FileMaker app that uses admin API to change the FileMaker settings. Okay, so first I'm going to log in to request access. Then I'm going to enable SR. Okay. Now I need to restart FileMaker server for this to take effect, okay? Because the setting got changed. So I'm going to start FileMaker server. Okay, before I start it again, remember there are 3 databases, right? They got corrupted. So now I'm just going to copy from my backup folder, all right? So here I'm just doing a simple copy from my backup folder to the FileMaker database folder, okay? So now we got a good database, so I can start FileMaker server again. Okay, it's up. So again, I need to double check a couple things. Okay, first I want to make sure it's really enabled. Okay. So here, if it's enabled, you'll see something like this. So, okay, so database server started with startup restoration enabled. Okay. So the second thing I want to check is the database, make sure they are open. Okay, so they are all in good state, okay? So now I can rerun the test again. I'm going to launch my FileMaker Pro and open my test database. Then again, run with 5 users. Okay. Okay, it's working, it's getting busy. So now I'm going to start kill FileMaker server. Okay, it's killed. Okay, now I'm going to restart FileMaker server. All right, okay. Okay, started. Now let's log in back to admin console again. And we will check the databases. So as you see, all databases can be opened now this time. Okay? Okay. Thank you. The last thing I want to show you is the restoration status in the event log. Okay? Here is reported that the restoration has started and completed with no issue. Okay, so as you can see with startup restoration, your database can be restored and back online automatically after a server crash. Okay, thank you. Back to you, Dan.
Thanks, Ming Chen. That was a lot quicker than having to recover your files, right? If anyone want to go back to the other way? All right. All right, so let's take a minute to become acquainted with the actual startup restoration log and some of its behaviors. So the startup restoration log, it's an 8 gigabyte file, but it's actually comprised of 4 smaller 2 gigabyte files. Okay, and these files, they represent all of the data from all of your hosted custom apps. Okay, so you can't create additional instances and point them to different data sets. Now, the way it works is that data is going to be written to that first log, and it's going to kind of snake its way through to the other logs. Now, Murali mentioned previously that the underlying architecture, it isn't fully ACID compliant at this time, so these changes aren't being made in a transactional manner. What I mean by that is that data isn't being written to disk before it's committed. So instead, what's happening is that data is being captured in the log asynchronously, okay? So about every 2 seconds, what we're going to do is we're going to look at that log. We're going to look at that data between that head pointer and that tail pointer. We're going to say, okay, what data was actually written to the disk? We're going to find that. We're going to remove that. And then we're going to move the head pointer appropriately forward. Now, you may be wondering, well, what if I fill up that log before any of that data is written to disk? Well, if you fill up that log before it's unwritten to disk and you're about 75% full, what's going to happen is we're going to pause the databases. We're going to flush that data to the disk, and then you're going to start working with empty startup restoration logs. So here's kind of what it looks like, the startup restoration looks like in practice. You can see that we have some data moving its way from the first log into the second log. But now we're at a point where that first log doesn't contain any more data. So what's going to happen is that it's going to jump to the back of the queue. So you essentially have this continuous, logical, rolling structure that it just provided us more, better performance and more stability versus having everything in just one large log. Now, there is a reason why this is called startup restoration and not startup recovery. So essentially, what's happening with the startup restoration is that it's going to perform a consistency check. So you remember those pages that Murali was introduced to us in that B tree. The consistency check, it just takes a look at the pages, makes sure that they're linked appropriately, they're in order, and then we come in and fill the gaps where needed. Unlike the file recovery process, which actually looks into those pages, and it makes sure that the values in there are appropriate. So those are two wildly different things. The point is, think of the startup restoration tool as just another important tool in your toolbox. It's not meant for you to drastically alter your disaster recovery plan. In the interest of time, we could go really, dedicate an entire session to startup restoration, but we want to get to those performance considerations. So in the interest of time, we do have a really fantastic written startup restoration white paper. It covers all of the best practices and things you want to know about this particular feature. It's downloadable for free. We have a knowledge-based article dedicated to that. I believe you can get that from the FileMaker community as well. But before we move on from the startup restoration topic, there are two important things I want to talk about. We talked about the ability to enable and disable startup restoration through the admin API. Well, it's important to know that when you enable or disable startup restoration, you're equally enabling or disabling that page-level locking architecture that Murali introduced to us. Now, the decision behind that, we felt like if we're going to introduce this page-level locking architecture, if we're going to introduce this support for all of these multiple requests, then we wanted to tie it to something like startup restoration. You know, it was just a no-brainer to automatically put you in the most reliable environment. We will be talking about later on in a few minutes certain scenarios where it may make sense to actually disable the feature. Now, in terms of feature availability, in market today, FileMaker Server 18 will have startup restoration and page-level locking. FileMaker Cloud for AWS does not. That said, let's go back to the top of our presentation. These changes were driven by that future-forward thinking. So we're going to see startup restoration and page-level locking in the next iteration of FileMaker Cloud out this fall. All right, so that was just a really quick introduction to startup restoration. Now, in terms of performance considerations, obviously, the flip side to a feature that's constantly tracking changes and frequently writing to the disk, there's going to be some performance latency, right? But I want to create a wider picture of performance factors so that you're better equipped to take advantage of FileMaker 18's performance. Now, let's take a deeper look into page level locking, okay? And in general, these are the variables that you want to consider for performance. So we'll start with the single user versus a multiple simultaneous user environment, okay? And to help demonstrate this, let me take you back to that B tree that Murali introduced us to, okay? Remember, a B tree is just a representation of the physical data structure. Now, the way it worked in previous versions is that when a request came in, the entire B tree was locked. And you can see for this single user here, they make a request, and now they're traversing through the index pages to get to the appropriate data page. With page level locking, the B tree is no longer exclusively unlocked, and you can see that same request is traversing its way through the indexes, but now it's locking and unlocking its way to get there. So for a single user who's doing your normal routine tasks, adding a record, deleting a record, modifying a record, they're not going to immediately take advantage of the benefits of page level locking or the benefits of releasing pages. In fact, under the hood, there's actually a little bit more happening to get them to the same result. Now let's take a look at what it looked like previously with a multiple simultaneous user environment, okay? Again, the B tree, it was exclusively locked. And then we had a queue of requests that were just waiting to get processed, waiting for one process to finish, then the next one will come. With page level locking, you can see that now that we're releasing index pages, we're not exclusively locking that B tree. We're getting the environment where we're no longer waiting for requests to process. We have multiple requests traversing that B tree page, and more users are getting data faster. It's pretty simple, right? So between the two, generally speaking, your deployments where you're going to have multiple users, they're going to benefit much, much more than a deployment centered around a single user in a file at a time. Now, another important variable, how big is your file? So, for example, if you start creating out your file, it doesn't matter if you're a single user or multiple simultaneous deployment, no one's really going to take advantage of page level locking. There just isn't enough real estate for that to happen. But with larger files, okay, now maybe the single user may start feeling that additional locking and unlocking as they navigate through the file. But conversely, the simultaneous users, they're clearly going to feel the improvement of speed because there's just going to be more space for more requests to process. Now, the final variable is what type of task are you performing? So we did extensive testing for different scenarios, different user sizes, and across the board, these were the actions that had the most significant performance gain or loss. Really, the other actions here that are not shown, it just wasn't as significant, so it didn't make the list. Now, if we take a look at the right-centric column, what's happening under the hood is pretty much what was happening under the hood in previous versions. So from then to now, these tasks, they already had the potential to be a little bit slower. And now we have a little bit more context of why that is happening because of the locks that they're using and the single thread approach that they're using as well. But now, on top of that process, we're additionally writing all of those changes to the startup restoration log. So again, these tasks, they may not feel as fast as they were in prior versions. And now, we've come across a scenario where it may make sense to disable your startup restoration. So a heavy import, for example, right? You may want to disable your startup restoration, restart FileMaker so you can apply that change. You perform that import, preferably maybe at night or when no one is accessing your file. When that import is finished, then you re-enable startup restoration and then restart FileMaker so that, again, you enable that change. Now, under the read-centric column, you can see that finds are using logical and physical locks that allow other users to access the B tree unimpeded. So finds across multiple simultaneous user deployments, they're going to feel significantly faster. So in summary, those who are going to benefit most from this feature, that startup restoration and page level locking, it's going to be the larger deployments, which really, it kind of makes sense because we're trying to implement this feature to improve scalability. So they're going to be read-centric deployments with simultaneous users and larger apps. And then the fines that they perform are going to be much more significant. All right. That's a good time for us to stop, and let's open it up to some Q&A if you have some. Please start lining up to the microphone. We have Murali and Ming Chen here with us, but I'd also like to introduce to the stage FileMaker Server Product Manager Neil Wright and FileMaker Guru and Architect Clay Mackel. Yes, sir.
To get the full advantage of the new page locking, do you have to be running FileMaker Pro 18 in conjunction with Server 18, or does it just happen on Server 18?
It's just Server 18.
Yep.
Yeah, it's on the database engine level, so like it's a Server 18. Yeah.
So when you're talking about locking the tree, how is that realized by the end user? Is it in, I guess, them receiving commit locks in FileMaker as an end user, or is it realized more through the, I guess, the building of a queue to process requests?
So the read lock is usually only when the records are actually getting downloaded. So when you go to, say you go to a layout, there's a read lock that's put on the record's downloaded to the client, and then the read lock is released. When you click into the field the first time, well, not when you click in the field, when you click into the field and make the first change, that's when it goes to the write lock. And that's when the write lock goes through, and if that fails, that means there was someone else that had a write lock or an exclusive lock. It changes from the write lock to the exclusive lock when you actually commit the record or when you click out of the record.
Okay.
So that's how the user interactions map to the locks that he described earlier.
Okay, thank you.
Hey, nice job. Keep the improvements coming. Hey, in a traditional environment, you always pause the databases to execute a backup. In the environments we find ourselves in, more and more they're virtualized. And the preferred way of doing backups is to take a snapshot of the whole drive. They can do it fairly quickly. Now they refuse to tell us the schedule that they're doing those snapshots. Are there any implications if the database is throwing locks when they take a snapshot of the whole drive?
The locks are being used internally for when we're doing operations. The big thing that the pause operation does, it grabs the exclusive lock on the entire file, and then it flushes all in-progress work to the disk at that point. Mm-hmm. So it's really not the lock is the problem, it's flushing everything to disk, so when they take the snapshot of the drive, that they have all the actual data that was in progress or being done at that point. So really you somehow have to sync the snapshotting up to the locking or the pausing of the database.
Okay, so we do have to argue for some kind of synchronization then.
Right. If they can somehow inform us that they're about to do a snapshot so that you can script it, admin API or command line or whatever like that to do the pause and then stop it. Yeah. But at any point, we may have internal locks, but they don't know whether we have a lock, and they don't know if we're in the process of writing something from one of the logs to the disk. Right. And when the pause command gets completed, we've grabbed all the locks that Murali talked about and stuff like that. And then the key thing is that we flushed everything to disk at that point, and that everything needs to be on the disk before the snapshot happens, because the snapshot is not going to take a snapshot of memory. Okay. Unless it's like some bizarre case where they're doing like when you put the machine to sleep, where they're saving everything in memory too. I mean, if you snapshot the memory and the hard drive and you keep the entire state, but I don't think there's any. I'm not sure if there's any backup processes that try to use sleep mode as a restoration process, but if they do go that far, then that could potentially work with FileMaker Server.
Okay, thanks.
First off, we've seen tremendous speed increases with Server 18 moving from 17 to 18. But when our FileMaker server restarts, startup restoration fails, but we're still seeing these speed increases. Are we getting the benefits of the page level locking, or is this something else that's going on?
Well, the speed level startup restoration would tend to slow things down. So the speed increases is coming from the page level locking.
Okay.
And one of the key reasons why we tied them two together was that page level locking puts things more in play in memory. There's more things floating around at the same time because we don't have these big exclusive locks where you saw the entire screen red because only one person can work at it at a time. So that's the main speed improvement is coming from the page level locking.
Thank you.
Hello. I have a question that may not be appropriate, but I'm here, so I'm going to ask it. Is it possible to establish a way that an administrator could unlock a record that an individual is in, so that instead of kicking them off the entire database, like just to even through a script step to be able to unlock that record so that I could potentially rerun the script and complete some action? Is that possible?
The clients would get terribly confused if they thought they had the record locked and then they got unlocked. Maybe we could try to abort the script, but you're going to really get into some bizarre states on the client depending on when the administrator said, oh, just release this lock and terminate that script on that user. Right now, the safest thing we found is when we get into these states that we can't return a consistent state of some consistent state is basically shut the entire file down so that they have to start from scratch. So you come back at a well-known state at that point. It would be a terribly complex problem, especially with how our scripting language works. It's so context-based to try to bail out just part of the context. Yeah. Then you're in a real unknown context state for the script engine, and things just get confused at that point.
Okay. Thank you.
You mentioned you get the more benefit with larger files, but didn't really give any parameters. Are you talking about in terms of the number of records or the physical size of the file? And are we talking about, thousands of records, millions of records, gigabytes of file size? At what point do you start to see the benefit?
Yeah, basically, whether you call it the number of rows, it translates to the number of pages in the B tree. So more rows, more pages. Okay. More pages means more levels in the B tree. So yeah, if you get into millions of rows, definitely you see the noticeable difference in the page level locking.
Okay,
yep.
Thank you.
Yep.
Is there any planned replacement for the standby server functionality, and would the restoration log be part of that?
So what was the question?
Yeah, the simple answer is no. I'm not going to lie. So no, we're not going to bring that back. We've got lots of other stuff that the team are working on, and you've seen some of the strategy this morning about cloud first, but obviously whenever we're talking about cloud first, what we're talking about is server in the cloud first. So although this team ostensibly is the on-prem server team, we're also the cloud server team. So a lot of the stuff we're working on right now is purely around performance, scalability, resilience. So that's this team's time is really focused on that side now. So sorry to say it, but no.
Hi guys. The 8 gig restoration log file, is there a reason why it's 8 gig? Is there anything we should be aware of that if we've got say a server that's got hundreds of gigs of storage on it, does the 8 gig have any impact on that? That's one thing I wanted to ask. And secondly, we've done some tests on like 50 million rows with a page file, and we're seeing roughly about a 15 times increase in performance to the users. So just to let everyone know. So great work, thank you very much.
so Gary, you're saying 15 times?
15 times. So if you were doing a find on old, say 17 server, you're doing a concurrent search on that record or on that data set, we were seeing round about, it could take, on say an on-store calc or any sort of things, we were testing it, we were seeing around about, it took around about 20 minutes to do a search if you did concurrent on 17. And then on new 18 server with the page file options, it's going down to about a minute and a half. So.
That's phenomenal.
So
That's
it's
great.
phenomenally fast. It's
Excellent.
really, really quick.
Thank you.
So,
And just because he's English, I didn't plant him.
but the page file, the actual restoration file, is there an impact because it's 8 gig and the size of your databases we should be aware of?
Well, the 8 gig is really more for the amount of data that's in play. That's, you know, it's kind of like the buffer, you know, it's a temporary place where the log is going into, and as stuff gets flushed to disk. Now, if you really have an old, slow hard drive, you may run into the case where the 8 gig drive gets filled up before everything gets flushed. But with what modern, you know, SSD drives, you know, do we log out when you hit that case when the log gets full and you've paused it? Is there a log?
Yeah, we do that.
Yeah, there's a log.
Yeah.
Yeah, if you see that log entry coming up there, that really means your hard drive is probably too slow.
Okay.
You need a faster hard drive.
Yeah, we're not seeing that. I didn't know if there was a limit or there was any.
Yeah, that's what he mentioned earlier, is that if it gets to that point where it's filled up and, you know, the 8 gig wasn't enough, it's going to pause and catch up. But if you see that log entry come up, that means for some reason you're writing data faster than the hard drive can catch up with what's coming in.
Okay, cool. Cheers, guys.
And one thing about the performance improvement, they didn't mention that some of the future stuff is we've had these other optimizations that have been setting on the side waiting for the page level locking to come in. They aren't in the 18 release now because we just got the page level locking and the startup restoration in. So there will be more stuff in the future to speed up more operations, because now we can actually take advantage of having multiple threads being able to enter and edit and read pages at the same time.
Yeah, we did a sort test as well across the records. We didn't see that much of an improvement for sorting, so maybe that's not there yet. So.
Right, yeah, no, Find worked out easily without much change internally, but you know, we're looking at things like sort and stuff like that.
Okay.
And maybe summaries and stuff like that, though, that should start improving in speed as we, like 4 years ago, I did all this work to say, oh, let's make this all multi-threaded and stuff like that, and then found out that it didn't really improve in speed because the bottleneck was down in the lower level parts of the engine, and this is what Morali's been working on to speed up. So
that's great work.
We had to fix the bottom level first before we can, make the higher level improvements.
Cool. Cheers, guys.
Hi. I heard you talk about ACID compliance. Does that mean you'll be able to provide some kind of transaction system in the future?
Yeah, well, I guess this is part of the roadmap to get there.
Yep.
And much like I said, the speed improvements, doing more asset level type improvements and transaction improvements, we needed more support. This is actually more closer to the startup restoration. I mean, and originally when we started calling it, we called it transaction support, but it's not to the point of being transaction support. So that's why it's called startup restoration, because it can restore this part, but it is a rolling log that's going on in there. It's just that we're not generating all the other stuff that has to go around it to do rollback and all the other things that you see in other database systems. But the low-level technology has now been implemented and is getting executed. It's just we can't do everything at once, so we're doing things in stages.
Does this bring us any closer to being able to do failover and clustering of FileMaker servers similar to other database servers? And or having read-only slaves?
It kind of goes back to what Neil was saying before, is that this cloud architecture is changing some things of how the server works. So, yeah, that's coming in the future.
All right, thanks everybody.